We can now look at how indicators work and also how pH changes when we do a titration. So first of all, let's look at how an indicator works. Well, an indicator is actually a weak acid. So we're going to represent an indicator by HIN in a similar way that we represented a weak acid as HA. So obviously a weak acid is in equilibrium when we dissolve it in water with H plus and IN minus. And the key thing about an indicator is the acid, HIN, and the IN minus, anion, have different colours. So in this case, for example, the acid may be red and the anion, once it's lost H plus, green. And so we would know that from Le Chatelier's principle, if we were to add lots of acid to that, the equilibrium would shift to the left-hand side. So in acidic conditions, we would see red, and in alkali conditions, we would see green. So the pH at which the indicator changes colour will depend on the indicator's pKa, and when we have an equal concentration of the acid, protonated acid, and the anion present, then the colour is a one-to-one mixture of both of those. So in this case, if we have red and green, we would see an orange colour present. So we can work out the pH at which the indicator will change colour. So we can look at KIN, which is the equilibrium constant for the indicator. Halfway through, we know those concentrations are the same, and so KIN is equal just to the concentration of H+, and so the pH at which the indicator changes colour is the pKIN. So the key thing to note is that indicators will not just change colour sharply at one pH. They normally change colour over a range of pH. So for example, the two that we're going to look at in this video are Methyl Orange, which has a pKin of 3.7 and will change colour over a pH range of 3.1 to 4.4, and Phenolphthalein, we have a pKin of 9.3 and again changes pH over about a range of 2. So let's have a look at Methyl Orange. So that is actually the structure of Methyl Orange there, and that is the a protonated version, and that's in equilibrium with that anion there and H+, and it can be difficult to see where that H+ has come from, and it's actually that H+ that has been lost. Those are the two colours that we would see, so in acidic conditions we see red, and if we go to alkaline conditions, methyl orange is yellow. So how do we choose an indicator? Well, the equivalent point of a titration is where we've mixed the acid and alkali in exactly equal proportions. So we need to find that equivalent point. That's what we're looking for. And so we need to find an indicator which changes colour at that pH. So methyl orange has that range and phenolphthalein has the range there. So let's have a look at neutralization. So we're going to look at some titration curves, and they're going to show how our pH changes during a titration. We need an indicator that gives us a sharp endpoint over that sudden pH change. We're going to assume that these titration curves are the alkali is in the burette and it's being added to the acid. Obviously, if the question goes the opposite way, just reverse the curves. So this is what we would see if we add a strong acid to a strong alkali, and this would be an example of perhaps 0.1 mole per decimeter cubed sodium hydroxide being added to 0.1 mole per decimeter cubed HCl, and the volume of HCl in a conical flask would be 25 centimeters cubed, because we see neutralization occurring once we've added 25 centimeters cubed of sodium hydroxide. So we start with a pH of 1. Don't see much change during the first 20 centimeters cubed. We then see a very sharp change, and our pH will level off at about 13 once we have excess sodium hydroxide. So that's our equivalence point there, about pH 7. Those are our two indicators, and you can see that we can use either because they both change colour over the sharp change in pH. So for phenolphthalein, we would titrate just until it becomes pink, because that's the nearest to the equivalence point. For methyl orange, we would titrate until it becomes orange. Strong acid, weak alkali now. And again, we can see that we have very little change, but then a more gradual change once we've got excess alkali. And the alkali here we are using is ammonia solution. Here are our two indicators and our equivalence point. So we can see methyl orange and phenolphthalein. Phenolphthalein, of course, is no good here because it changes colour above the sharp change. And so methyl orange would be the one that we would use. And again, we would titrate until it is orange. Weak acid, strong alkali now. So we're going to start at a higher pH for weak acid, have a steady change in pH, and then our curve will level off at a higher pH than the one previous because we've got a strong alkali. Equivalence point is there. And so phenolphthalein is the one that we would choose because it changes colour over the sharp change in pH. And we would titrate until we see the first sign of pink. Methyl orange is no good. It has turned orange way before we have actually got a one-to-one mixture. And finally, weak acid, weak alkali, neither are any good at all. We have a steady change in pH. And so when we add, if we try to use either of those indicators, neither would actually work. So we can't actually use this in a titration for weak acid, weak alkali. And that concludes the video for pH changes during titration and how we use indicators.